We can go ahead and get started. This is our next topic on Internet of Things security, and I tried to track down the genesis of this particular quote, and it just seems to have been around for as long as the term has been around. So there's no individual person I can attribute it to. It's not anonymous in that sense. Just can't find a singular person. And the quote is the S in IoT stands for security, and that's meant to be like a bit of a joke. So we will talk about Internet of Things, what is the same from what we already really understand and appreciate about computer security and the hacking process, what aspects make it interesting and different. It's somewhat related to when we were talking about web application security, and we talked about, and we had a quiz question about, what aspects make web application security very comparable to more traditional computing and network security, and what aspects are really kind of differentiating it. In some sense, we can be fully reductive and just say, as we talk about some of the terminology and things like that, that it's just another computer. And you would be right in that somewhat reductive view of what's happening in the world of IoT security. It is, in fact, just another computer. And so, from a fundamentals perspective, there is truly nothing different. Just like from a fundamentals perspective, there is truly nothing different when looking at web application security. What I'll try to kind of tease out today and then as well on Thursday is, well, yes, ultimately it's just a computer at the end of the day. And the sort of hacking methodology may in fact be quite similar that we would employ to explore those devices. There's some characteristics that make it worthwhile to study as a separate topic than just the traditional aspects of computer security and vulnerabilities. Just as a very brief outline, so we will talk about Internet of Things security. Actually, really the first thing we'll start with is more of a definitional exploration. This is definitely a field in which, since there's no sort of governing body of Internet of Things in general, and the field as a whole has evolved from a few different perspectives. What you'll find is different people using different terminology to refer to what I think from our perspective is roughly the same thing. So while that may start a little slow, we'll make sure that we have a good grounding for the terminology you may find after you leave the classroom. And then we'll look at things like communication models and protocols. We won't go into a lot of technical depth on those. First off, I mean, some of that technical depth does require sort of advanced communications and signal processing skills that you may not have or may not be interested in acquiring as of yet. But I think an appreciation for the different models and protocols is an important thing to understand. Talk about what it means for an IoT implementation hacking perspective, what aspects are effectively the same as our traditional hacking enterprise, what is different, what makes it unique in the IoT world. And we'll touch upon the concept of botnets. We'll also touch upon that later. It's related, but not in as direct of a way as it could be. And so as we talk about other malware sources and characteristics, we'll also talk about malware before the end of the semester. This week, as you have been finishing up or have finished up Lab-09, it's also another example like with our physical security lab, because everything is virtualized, you don't really get to see the of things aspects of the IoT hacking. It's more of a botnet lab than it is an IoT hacking lab. From one perspective, you can just think of them as lighter weight images that you're exploring versus just the more heavyweight Ubuntu or Windows images that we are otherwise looking at. So you should be finishing up that lab now. For better or for worse, the way labs 8, 9, and 10 were structured, you can't really get too far ahead. So I can only really deploy lab 10 stuff by pulling out the lab 9 stuff. So you can't really start early. There weren't a lot of people clamoring to start early, so maybe we've hit a good steady state this semester. So it should be the morning of your lab. You should be able to get started if you wanted to look at that technology. You can always read, though, as it becomes available on Canvas. You can read about the lab and understand what you'll have to do for it. Lab 9 I thought was relatively straightforward. Lab 10, I think it's also relatively straightforward. But as always, when you have questions, let your TAs or myself know. So as I mentioned, we're going to start with a little bit of discussion of initial terminology here. There's a lot of terminology on this slide. Whether you need to memorize it now, probably not. It's not something I'm going to explicitly quiz you on either. But I think just as you come across this bigger, larger field from different perspectives, you're going to see some of this different terminology used by different people. And I just want to make sure you understand it would be too reductive to say it's all exactly the same. I don't think that's a useful way to phrase it. There's a lot of overlap there. I'm going to do my best. If you're still not totally certain, you can ask questions, or I'll try to come back to this later as well. The first term I have in there is referred to as embedded systems. Is anyone here taking the embedded systems class? It would be mostly cyber E's, CPREs, and some SEs choose to take it. Um, Embedded systems appears to be a term that's mostly being used these days in sort of the educational space. That's been my experience with it. And you take a whole class on it, you get a whole semester worth of definitions, and we have multiple embedded systems class. Definition that I work with, it's a computing device that is part of and interacts with a larger physical system via sensors and actuators. Now, if you take 288, you know all about sensors and actuators. If you haven't taken that class, that's fine. Things that can read in information from the outside and can also make some things happen on the outside. For want of a better way of thinking about it, motion sensors and motors, right? Can read in the information from the outside, can do something with that by driving a machine or doing something physical or control a robot arm. And when we say embedded system, that's really all it means. It's a computing device that is part of a larger system. The word embedded means, as the English word implies, it is part of something larger. It is embedded in the larger physical system. That is meant to be in contrast to what we would refer to also in kind of the educational context as a general purpose computing system, which is not embedded in something larger. It is just something meant for general computation. The other term you would see maybe more in commercial usage of devices that you buy is this concept of a smart device. Smart device is absolutely an embedded system. One is more of sort of an educational definition. One is more of sort of a product definition. A smart device is an embedded system that has some general autonomous function and can also generally connect to a network or the capital I internet. Smart device is meant to be contrasted to you may hear the term dumb device or traditional device. That's all that means. You have a regular refrigerator, and the refrigerator's job is to keep your food at the temperature you require. Now, in practice, that refrigerator has all sorts of digital circuitry in it. Whether it needs a microprocessor or not, it's hard to say, but traditional fridges of the type you buy today are just there to serve that individual purpose. And you also have a smart refrigerator, where it's also doing that initial intended purpose, but maybe it can detect when you're low on milk and can automatically order milk for you. You'll find amongst computer scientists, computer engineers, kind of a bifurcation with regards to their appreciation and usage of smart devices. There are those who go all in, I would say, who love to have that level of programmable control over their life and their surroundings, and just love technology. And then you see the exact opposite extreme as well. Those who know just enough about how bad most software is, how flaky most hardware can be, that they want none of it, and they'll have the dumbest house, the dumbest device, the dumbest car possible. I have a colleague here who still uses a flip phone, and it's the only person I know who uses a flip phone still, and he's a professor in computer engineering here in this department. So you see both extremes there. So embedded system, smart device. The term, I would say, is more of a researchy term, so you would still see it in your classes, but probably closer to the 4,000 or maybe the 5,000 level is this concept of a cyber physical system. Here, it is more of a way of thinking about a design or analyzing a system versus actually being anything truly different than a networked embedded system. But one way you can think about this term, cyber physical system, is you do have this network of smart devices. And when we think about CPS or cyber physical system, again, it's more of a research term that you will see. It has to do with how we think about and model and analyze how the computation directly interacts with the physical aspect of things, and vice versa, potentially how the physical world can interact with computation. If that sounds kind of fuzzy, that's okay. It's a research term and it's meant to be a little bit fuzzy. I think for your purposes, if you see the term CPS or CPS security, it's not the same as a smart fridge security, but it's not that different either. So you're in the same ballpark when you're thinking about cyber physical systems versus smart embedded devices. I said smart device. Then if you just kind of extend that context a little bit further, you have things like smart home or smart grid. So if your home is embedded with these smart devices throughout, you can have smart lighting, smart heating and air conditioning that are all controlled Generally, the assumption is via some sort of network accessible, some internet accessible software. I have an older smart home that we purchased. It uses X10 automation, which nobody really uses anymore, that works over power line. And for some reason, I'll run on my treadmill. If I run for 3 miles, it's perfectly fine. If I run for more than 3 miles on my basement treadmill, it turns on one light on the top floor of my house after I've run for more than 3 miles. I have no way why that's the case. I wouldn't say it's too lazy to determine why that's happening and try to track down. I really don't have the technology to try to track that down. What's that happening? Why that's happening? At some point, some signal the treadmill is sending for either power save or some other thing is somehow triggering a controller that's saying, turn on this particular hallway light on the top floor. It's not a big deal. I just go upstairs and turn it off when I know I've gone on a longer run, but that's old school smart home. Modern smart home is supposed to be a little better with regards to that, but it's just a home embedded with these smart devices. Lighting is the most common use, but air conditioning, heating systems as well. Then you have smart grid as well, and we will talk about that. It's an electrical grid that incorporates a CPS or a series of embedded smart devices for both the management side and the protection side of things, for metering as well. And then finally, again, as you're seeing, there's a lot of overlap between these definitions. We have this concept of Internet of Things. It's a network of smart devices that connect with and exchange data with each other. Now, the term is referring to the fact that there is an internet of these things. That's all that that term means. And even that's not really precise either, right? Another way to think about it of Internet of Things just means a large number of smart embedded devices. That's all that Internet of Things, that there are enough of them that in some sense they comprise their own type of internet. That is not to say that an individual device is an Internet of Things. The other term you would use to refer to that device would still just be a smart device. The other term you'll hear is IoT device or just networked embedded system. Those are pretty much interchangeable terms. So you have an IoT device. It's a little wordy when you think about if you're breaking that down word by word. That's just how the terms have kind of evolved. There's no one semantic authority saying here's how you must refer to these things. It is all referring to effectively the same thing. You have an individual device that is a smart device or an IoT device. Then, taken in a broader view, Internet Things refers to a larger system of those connected to the device, connected devices, and as well as the actual devices, their connection to some network and or internet and or cloud platform. That is not to say that to be an Internet of Things, they all have to be working in concert. Some people think of it in those terms, but it could just be the sum total of a given system, municipality, home system of those devices, and the number of devices that those comprise. And then separately, if the resulting network of devices is then part of some broader controlling system, then you may hear the term cyber physical system become more appropriate for it. Is a cyber physical system an Internet of Things? I mean, yes, it's just different ways of describing the same context. If you don't see the term cyber physical system, which is becoming more and more limited to kind of power grid and cyber critical infrastructure type things, the other term then you'll see now is smart XYZ, where smart home, smart factory, smart city, smart farm, things like that. In the educational realm, you may also then hear the terms like wireless sensor network. We have a class called wireless sensor network, or pervasive computing, and they're just all very closely related concepts. I don't want to be too reductive, as I mentioned, with regards to this. Ultimately, when you hear any of these terms, what you're really seeing, what you're really referring to, is some sort of embedded CPU, an ARM processor, an ESP32 processor with some sort of attached sensors and actuators, some way of reading in temperature data, or some way of controlling a relay to turn on your heating and air conditioning system, usually running some relatively bare bone operating system while also connecting to some cloud-based service over the internet. And if you have that, you're in this realm of IoT. You're also in the realm of smart devices. It's all the same thing. So you have your Nest thermostat. Underneath the hood, you have a ARM CPU and some sensors and a simple controller. You have your smart light bulbs, which are almost all running some sort of ESP32 underneath the hood. You have your Alexa devices. That looks like some sort of Texas Instruments chip. Almost certainly it's an ARM microprocessor. That system looks pretty comparable to the CPRE 288 system. Same with your Ring doorbell. Same with your Garmin watch here. What do they all have in common? They're typically not running a general purpose processor on them for just practical reasons of sort of size, power consumption, efficiency. They are running, although the level of ability is kind of growing quite rapidly and kind of starting to even out, but generally they are running a lower end processor. It's able to do less stuff or less things per second than what is in your workstation PC, is in your current laptop, probably less so than what is in your cell phone now as well. Running some embedded processor has some sort of networking stack, of a nature embedded either in the CPU or as part of some peripheral devices here, and it has some mechanism by which it is interacting with the physical world in some way. As simple as controlling LED drivers for an LED light bulb, or um, reading heart rate data in the case of the smartwatch that we have there. They're different. They're different devices. They have different spots in the design space that people are trying to control for, different price points. They're actually quite similar at the end of the day. And I know that when you take sort of an introductory embedded systems class, you don't focus very much on the operating systems aspect, in which case the security profile is significantly different if you're running just kind of bare bones, standalone, bare metal kind of code on those systems. But in general, for just practical perspective, once you have a networking stack, yes, you can do it without an operating system, but much more commonly, there'll be a slimmed down, smallest capability possible operating system running on those, some sort of embedded Linux generally running on those, and then it's going to connect to some software service over the internet. That is our IoT device. That's what we're going to talk about here. A little bit more about what I meant by sensing and actuation. This picture kind of shows it sufficiently. Sensing, and again, if you've taken embedded systems class, you should be aware of this, should know this already. Converting some measured physical quantity into an electrical signal that can then be used by a computer. Generally also involving some potential analog to digital conversion as well. I have some determination of, what would be a good example here, um, a, uh, a flex sensor here. It's going to give some analog signal based on how much that particular piece of hardware is bending. It has some custom sensor circuitry to allow it to do so. I then, as part of my sensing task, have to take that electrical signal, convert it to some digital value that I can do some processing on. That is sensing. Reading in from the outside world is sensing. Then on the flip side, you have actuation, causing something to do something, to operate in the physical world or to create some physical change and or movement. The actuators tend to look kind of less interesting. These are not to scale at all here. Something that rotates or something that drives a motor that causes something to do something, to open a door, to drive to this location. Generally, with our high-level IoT architecture, so you have the things, whatever the physical thing that we actually care about, we have the sensors and the actuators. We then have our embedded computing device here. I brought a random Adafruit circuit playground, but they all kind of look the same. We don't really need to look at this one. Generally, although this is not a universal rule, there is some light data processing and storage that is happening on the device itself. Sometimes the other term you'll hear for this is referred to as edge computing. Um, the computation that's happening on the embedded device itself. Other scenarios will involve there being some sort of gateway device, not necessarily a network gateway, but it can also serve that purpose as well, in which the edge devices, the embedded computer devices, are really just reading in data and forwarding on to the next level. And then there's some other intermediate device that is doing the actual computation, or the work is just getting sent off somewhere to the cloud, to some existing cloud services, some internet accessible workstations and computers and servers that are doing whatever sort of heavy collation of data and processing and potentially determining what needs to be done next. If it's just a smart like thermostat. A lot of that can be done locally, but not all of it, right? Smart thermostat may be able to detect that the temperature is reading this value. You have a setting that you wanted at this value, and consequently, it needs to turn the air conditioning on to kind of do a control algorithm to lower the temperature. But perhaps then you have some internet accessible configuration for that, and now it needs to go off to the cloud to determine, well, actually, it's Tuesday, and I don't want to run the air conditioning on Tuesday. So that additional decision making has to happen somewhere else along the way. The reason we do not all and sometimes very little of the computation at the edge on these embedded devices, maybe it's not that obvious in looking at it, but they tend to be small, right? Form factor matters for all these devices here. One could build a smart light bulb that you can fit like a workstation size computing infrastructure into, but no one would buy that generally, right? Because you need to fit inside the light bulb. That limits what you can have there. Same for these other devices as well, right? We could put a supercomputer on a watch. It's just probably not a good idea in terms of people wanting to purchase it, right? They tend to look small, right? They tend to look, you know, 1 square inch, 2 square inches, 4 square inches, something of that size, right? That limits what you can do with it, right? That limits, if it's battery controlled, that certainly limits the size of a battery that is feasible for such a device. In terms of just raw transistor count, right? These things take up space. Individually, they take up a very small amount of space measured in nanometers, but you then have billions of these transistors in these CPUs that then does add up in terms of the physical space, the resulting analog circuitry required to provide reliable power to these things. Smaller, not always, but generally means less computational power. So why does less of the computation happen here? They tend to be not impressive in isolation in terms of the computation they can do. They're designed to be sufficient for the task at hand, but you wouldn't want to use it as your daily laptop driver, right? You wouldn't want to be your primary computing system that you are using. Depending on the device, I wouldn't want to totally make a random guess. But for the smart, Nest and the Alexa and the Ring cameras, probably some CPU running at, let's say, 200 megahertz, something along those lines, versus your Intel, AMD, or your Apple ARM processor running at 2 gigahertz, 3 gigahertz. Something in the smart light bulb is probably running at 1 megahertz. Much more bare boned in terms of the computational ability of it. That also has implications then for the security model of these IoT devices. That's one thing that makes this a separate topic than just computing in general. That's one aspect. Once you have the assumption where some of the critical computation and things we care about are happening here, but this is not something in which we can assume this device can handle perhaps the latest and greatest of cryptographic protocols. That then kind of changes the concerns about where we are in the security space. If we can't run the latest and greatest protocols, cryptographic algorithms here, perhaps we have to go back to simpler, more performance amenable type of algorithms, things of that nature, where we can have an operating system, but perhaps we can't have all of the security features of a full-blown workstation server class operating system. We have to make some trade-offs, or trade-offs in practice happen to get made for those particular devices. Other reason we care about IoT devices, separate from just what we've already been learning about, one big reason, and probably what can be your primary takeaway for why we care about IoT and IoT devices, would be that of scale. Again, there's some definitional issues here we may have seen. And when people say, non-IoT and IoT active devices and trying to project that out, it's certainly in the billions of IoT devices. It's a staggering number. You may just want to just consider your own just personal, computational wealth. What do you personally own in terms of computation? I would not count your cell phone as an IoT device, although it can in some ways act in that way. I would not count your laptop as an IoT device. Anything else you own that can connect to the internet probably counts as an IoT device for the purposes of this. We can talk all about edge cases of the definition until we're blue in the face. That's why you can take those numbers as just some sort of estimates. I think oftentimes people are just talking about laptops, workstations, servers in one category, everything else in another category. I think no matter where you decide to draw a line there, whether it's fuzzy or whether it's a bright line, there's a clear trend that is happening. So the one reason we care about IoT security, and I think this is valid, is the scale, the number of these devices that are available. There's a ubiquity of these devices. That has security implications in and of itself, right? Just number of devices itself is something to be concerned about. If I sell, 20,000 laptops of a particular model, well, they're going to have different configurations on them. There's going to be different user profiles of them. There's no one particular attack that's going to have any chance of working on all 20,000 of those particular devices. If I sell smart light bulbs instead, that can easily reach into the millions, depending on the brand. And even if they're different brands, they may be the same exact device underneath the hood. That can easily reach into the millions. They're not something that people sort of are able to or consider configuring after the fact. They are all probably running the same exact firmware after initial deployment here. If there's a vulnerability uh, in your workstation, a particular workstation model, that's one thing. It's still a concern. It's still an issue. It has to do with particular software configurations for that laptop. If there's a vulnerability in the firmware for a smart light bulb, you may instantly have a million devices. So when we talk about eventually talking about botnets and the like, that's why we kind of start to introduce it in this topic, right? If I know I have and can find a million devices that all have a particular vulnerability in them, and they're all effectively identical, that can be the genesis of a very powerful botnet for that very reason. So scale is one of the primary reasons why we cover and talk about this topic. The class of vulnerabilities tend to also be a little bit different. This is perhaps due to sort of market reasons and not necessarily technical reasons. It just so happens in practice, and we can maybe talk a little bit about the market reasons of it, that there's a lot of price pressure on these devices. Maybe that's one of the primary reasons, that if you have a smart LED bulb, you can sell it for $10. You cannot sell it for $100, no matter how nice of a smart LED bulb it is. That applies some sort of downward pressure on the whole design flow of these devices, both the hardware as well as the software associated with them. So when we talk about kind of a standard OWASP concern of insecure design, that just tends to happen more or in more publicized ways for these IoT devices. There tends to be cost cutting on sort of the software side of things with regards to these devices. When you add to that the fact that kind of by definition, these are meant to be highly network available devices. My smart light bulb needs to always be network available, or it doesn't serve its purpose. If I can't automatically turn it off over the internet, it's not serving its purpose as a smart light bulb here. And a little bit related to that, that while they are network available, they tend to, in practice, not have regular maintenance and updates. There is not an IoT operating system distribution that people use. There's the basis for them. There's kernel images, there's kind of bare bones Linux OSs that people start with, but there's not an Ubuntu of IoT devices. There's not a regular patching and maintenance regimen for these devices. Occasionally, when very important vulnerabilities are found, then there is then a flurry of patching and maintenance that happens. But in general, it depends. It's not the case for all of these. In general, even today, 2024, you buy your smart light bulb. It has some very bare bones stripped down operating system on there, some network stack that was copied and pasted from a prior project, has whatever software is running on there, and that's all you're going to get. And it's going to stay that way for the life of that light bulb, which presumably, if it's an LED bulb, 10 years is not a stretch. I think it can happen. So that's the second reason we care about IoT device security. There's some sort of market pressures leading to maybe sloppier software practices, or perhaps it's hardware companies kind of dipping their toes more into software as they're creating these devices. And then this thought of it's not an expected design or usage flow in which you are patching your light bulbs in your house because there's a new image for your light bulbs. And then the third reason we care about this, and this goes into that definitional game of cyber physical systems and the like, is that there's potentially unique attack surfaces, um, both due to the fact that there's some specialized designs, and also potentially some of these internet accessible smart devices are connected to high value targets. Talk about smart grid or cyber physical system security of the electrical grid. Those are networked, embedded computers, and they're attached to an extremely valuable resource. And so they're a target for that reason. So that's kind of the three reasons why that's the case, why we care about it. And in general, the core problem is you have this sort of design philosophy, development, and market pressures that wind up being the end result that focus on cost, time to market, power consumption, things of that nature first and foremost. Security as not an afterthought, but maybe a secondary concern for these devices. And so when you have the quote in the first slide, the S in IoT stands for security, yuck, 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 or Internet of Insecure Things is a term you'll also see. That's kind of what people are getting at. That you have these billions of devices for which the things we have learned through trial and error and generations of vulnerabilities and exploits in general purpose computing, those lessons learned not being applied to these devices necessarily. And perhaps if we care about raw headcount, raw numbers of devices that are potentially vulnerable, it's a bigger problem than all the other aspects of computer security we've been talking about. And they are connected. There's a veritable smorgasbord of networking standards. Again, this is not a networking course. We do need to talk about wireless networking security before the end of the semester. Probably our best case learning outcome is just some additional fluency of understanding the various wireless networking standards here. Some would be connected via traditional wired Ethernet, um, depending on the need and if that's even an option here. There's all sorts of Ethernet over power and power over Ethernet, so people can wire up a smart home where it's using Ethernet to kind of connect all these devices. You will see all sorts of these devices that can connect over what I refer to as sort of traditional Wi-Fi. If the networking standard starts at 802.11, there's still like 15 variants underneath that, but that all kind of falls under this Wi-Fi branding, all the variants there. There are then all sorts of what we call specialty wireless personal area networks that fall under the 802.15 banner. Doesn't always mean Bluetooth, but that's kind of the starting assumption that if it's got this additional wireless networking capability, that's Bluetooth. The other term you'll see, Zigbee, is very common in industrial automation as well as in home automation. There are many, many others of these technologies. Z-Wave was a very big deal back in the day. 6LoWPAN is another one that is popular. What's interesting, at least to me, about all these different networks is not memorizing which part of the IEEE standard they're in. Is not necessarily understanding from like the physical layer what they are doing differently. But to me, what I think what's interesting is where they kind of sit in this two-dimensional, and there's maybe a third dimensional here as well, of design space of how much sort of physical network connectivity they provide for you, as well as what kind of throughputs they provide for you. That's why there's not one size fits all. It's not as simple as saying, why not just slap Wi-Fi on everything? That can make some sense in some context, or why not, and conversely, why not just slap Bluetooth on everything? If you look at this chart, and it's maybe a little fuzzy to you on the screen here, you can look at it later in the slides, you see that Wi-Fi and Bluetooth, at least on this logarithmic scale of the X and Y axis here, X-axis is range, roughly, don't hold me to very particular numbers here, I didn't generate this plot, roughly what is the order of magnitude distance one can reliably do a point-to-point connection on the x-axis here. On the y-axis, a logarithmic plot of the rough order of magnitude data rate that one can achieve with it. Taken amongst all the different kind of wireless standards for IoT devices that people can use, Wi-Fi and Bluetooth are actually quite similar on that chart in terms of what kind of data rate they provide. Now you may say Bluetooth limiting to a few hundred kilobits or megabits per second versus hundreds of megabits for Wi-Fi. That's quite a bit different from a practical perspective. Sure, that's the case. But in terms of the range they provide, they're relatively limited, right? Really depends. Depends on line of sight. Depends on how many walls are in between, how far your Wi-Fi signal can travel. If you have tungsten in your walls or something, um, but it's relatively short, which may be sufficient. I'm not going to ever say one of these is better than the other, right? They're design points in a larger multi-dimensional design space here. Sometimes, though, for our IoT device, we need very little bandwidth. We're reading just a single value every so often, but we need to very reliably do it over a short period of time. Then perhaps one of the more low energy examples might make more sense here. Or RFID is a little bit unrelated to it, but maybe something like your Zigbee or Z-Wave or Bluetooth Low Energy start to make sense there. On the flip side, perhaps absolute range is our most important consideration. Well, there you have both the licensed and the unlicensed low rate wireless personal area networks. Um, LoRa is the only one I'd actually heard of before I put this slide together, but things that at least in theory are able to go tens of kilometers in terms of range. Still very low in terms of the amount of data rate that is possible here, but there could be all sorts of scenarios where you're doing sensing of ocean currents and things like that. You need a very large potential range. You can't put signal repeaters every few hundred meters in the ocean. That allows you to maybe do that kind of sensing at a scale that otherwise wouldn't be possible. But ultimately, you're not reading and writing a lot of data when you're doing that. A few bytes here, a few bytes there, something relatively slimmed down is going to be sufficient for you. Or if you really need both, kind of maxing out both throughput as well as potential range, now you're talking about the licensed cellular bands, your 5G, your 4G LTE, things of that nature. There's also kind of the third dimension here is cost. Cost means a couple of different things. Cost in terms of the standardization efforts and what it costs to actually ship a product that is compatible with one of those things. In terms of cellular data rate, there's then also typically costs associated with subscribing to a company that provides that infrastructure to allow for that. But that's why it's not a straightforward thing to say, an IoT device is a network embedded computer. It is. It is correct to say it, but it's just not sufficient to say it. What kind of networking are we talking about? And there's going to be different security implications depending on the use case of the device and depending on the resulting part of the spectrum and what specification it is adhering to. For now, and even later in the semester, when we kind of touch upon wireless security as a separate topic, I think awareness, familiarity of these different versions is probably going to be sufficient for us. You should never be scared about any of these in the sense that they're different parts of IEEE standards. They use different frequency bands, but they're all just networking stacks at the end of the day. Right? They still follow roughly, your OSI or your TCP/IP version of the networking stack. The software and the resulting algorithms at each level are different for these different versions of standards, but they're not that different. So awareness, familiarity, knowing that I have this device. What are either I'm building a device or I'm analyzing a device? What are its needs? What is its effective range? What are the trade-offs between how much throughput it can get versus how much battery life it's going to have correspondingly to the amount of power consumption there? Those are the kind of things you can start to analyze with this sort of analysis, but we don't necessarily need to go into all the double E signal processing and the communications algorithms underneath the hood. In terms of consumer IoT, there is just smart, all sorts of things. That's your smart doorbells, cars, smartwatches, smart thermostats, your smart coffee pots, HTTP error code 418, kind of a joke in terms of it was originally intended as kind of a tongue-in-cheek joke that in the very earliest days of the internet, there was an attempt at an internet-connected coffee or teapot, I think was the case. So it's sort of a real thing. It was encoded in early versions of HTTP specification. You can go to google.com/teapot and you can get 418 error code back that I am a teapot. That is to say that these kind of IoT devices are almost as old as the internet itself. Well, what are some of these security concerns? separate from this, why do we care is also a security concern. What are security concern of having a smart doorbell? Sure. Absolutely. And do what? Absolutely. Security and privacy, of course. I said security concerns, security and privacy concerns of that video feed. That's become kind of an interesting, sort of political, controversial topic, right? These programs at Amazon requests that you enroll in that say you have a Ring doorbell. Would you like to share your feed to local authorities who are trying to track down a suspect? And I don't know how I feel about that, right? I mean, it's my video feed. It's not Amazon's video feed. I want to kind of keep it private, right? Absolutely. What about smartwatches? What security or privacy concerns there? Absolutely. Certainly, by default, I think for the most part, if you use a Garmin, Apple's probably better on this. I'm not as knowledgeable of the Apple health ecosystem. They have found that all sorts of troop movements can be shown via just looking at public Strava and Garmin data saying, or Secret Service movements saying, well, they like to go for 6 a.m. jogs. Oh, look where the Secret Service is today, because they've just posted inadvertently where their actual location information is there. What other examples here? Smart locks, I guess, is kind of obvious in that sense that we understand that now. There's the physical security of lock. Once it becomes a smart lock, it's either in addition to or in lieu of the physical security of a lock. It now turns physical security into kind of a cyber security concern. And if there's vulnerabilities there, obviously that's an issue. We can think about connected cars and the concerns, and we'll talk a little bit more about that as well. I mentioned Smart XYZ. Smart cities is an attempt to sort of manage a city's assets through networks of IoT sensors. What tends to happen in practice is, you have these municipalities, these cities that have existing infrastructure that has to be updated and modernized. And right around 2010, a lot of these cities realize, well, we have to replace all of our street lamps anyway, our street lights anyway. We might as well, in replacing it, consider making them smarter. And these are just 3 examples. There's many such examples. There's, for example, San Diego decided to build smart streetlights. We talk about security concerns here. San Diego built out, I was trying to find a better picture of it, from their typical streetlight. This is still a streetlight. It doesn't really look like it anymore, right? But big LED light. What did they decide to add to it? Well, add a smart device, not so dissimilar from like a Ring doorbell, but some sort of 360 camera here. I guess the thought is if you're already refreshing a street light, you have kind of a guaranteed power source at that location, right? So it's maybe less retrofitting and you already have kind of a mechanism where they're kind of already physically present. Less overhead to kind of replace those devices versus trying to add new devices here. But these were meant to be for security purposes, for policing purposes, and the study showed that it was effective from that perspective. It showed that by having these in every single street light that they replaced, they had basically camera data that they can then feed, that they can tap into those feeds as needed here. And they even make the claim, well, these video cameras are recording crimes in public places, principally streets and sidewalks, where there's no expectation of privacy. That's kind of a legal determination that's been made over a period of generations. If you're out in public, you have no right to privacy. And also they're trying to blur, to mask people and license plates and things of that nature. And it claims here that when it was used, facial recognition was not used with that technology. This is a few years ago. Certainly if it was done today, there'd be some machine learning applied to this. It would also be doing facial recognition. This is an interesting example in which this was a municipality that implemented all of these, and they decided this was more of through a political process that they shut them all down. They said, we don't trust authorities having access to this type of surveillance in our city. And so even though the technology was capable, there was enough concerns about privacy, maybe security vulnerabilities as well, that they then wound up shutting it down. Another example, which was also smart streetlights. This article isn't the best one, but they used low power wireless personal area network, LOPAN, 6LOPAN, that they were retrofitting also all of their streetlights. and that basically provided municipal Wi-Fi. Again, the idea is you already have probably a few thousand of these street lights throughout your city. They're already there. They already have a guaranteed kind of power source coming to them. You have to replace the bulbs anyway to go to LED bulbs and the like. Let's add a wireless mesh network to those devices. There, the trade-off was, if we look at 6LoWPAN on this trade-off here, there's a few different versions, and I couldn't see exactly which one they were using. Probably not as good as what your cellular connection would be able to provide for you, but as a free kind of municipal connection here, both for reading other kind of decentralized data sources as well as for potentially consumer use. That's still kind of a nice capability there as well. One final example, and we can actually leave things here for today. This is San Francisco, that their IoT device that they implemented was a little bit different. See if I can find a picture of it here. This was a smart parking sensor. So it's a puck that they kind of just embedded in the ground physically here, with a little adhesive, I guess, that would just detect if there was a hunk of metal above it or not. That was the sensing that that thing was doing. The idea being then you can get kind of real-time uh, parking information and kind of live updated versions of parking information. These days, if this was to be rolled out today, I would imagine they would almost certainly use like camera technology instead. But still, this kind of approach is pretty effective. Can detect if there's a car immediately over it using the 928 band, which if we go back to this diagram here, is in this band here. So it doesn't need a lot of bandwidth, right? It needs to just basically send every so often information saying car parked, car not parked here. And then they would have to have kind of these localized gateway devices that would collect that information and then send it off to the cloud to kind of collate all that information. This experiment, I believe, is also not in use anymore. Roads don't last very long. I wondered why, and then I looked at this map of San Francisco. And this is right where my car got broken into this summer. So I think no one wants to park here anyway. That's maybe why it's not in use. Um, let's leave things here for today. Well, we'll kind of finish up this topic on Thursday and come back for our quiz as well. We'll talk more about IoT in the meantime. Thanks.